Good morning, everyone. I hope you guys are having a good start to your day. Today is the 9th. We have 3 weeks and a day until Halloween. Um, Bring that up because my kids are really looking forward to it. And I'm now beginning the process of saying, no, we can't get candy because, Halloween's like right around the corner. Um, it kind of works. I'm better at that than my wife. She's more like, okay, okay. And I'm like, nope. I'm a grouch. Um, but anyway, it is the 9th. We're gonna go ahead and get started. We're talking about the mole today. Um, I graded your first homework. I posted all those grades. I'm gonna be posting a second and third homework assignment later today. And I'll post an announcement with those. One thing that I wanted to remind everyone was that the homework is going to require your own penmanship. Now, whenever I say that, that doesn't mean that it has to be like printed up and written on. If you have a tablet, for example, like a what was it? If you have an iPad or something like that, you can write. You can use your stylus to write. I don't want typed answers though. I want you guys to write it. And if you're thinking like, how am I supposed to do that? Well, one thing that you could do is just get, a blank piece of paper, write question one, and you don't have to write the text of the question. Just write your answer to that. Um, so. With that in mind, one thing that I want you guys to know is that the I'm going to drop at least one homework grade and I'll drop at least one quiz grade. But I'll be posting some more stuff for you to go over or some work for y'all to do prior to our next exam, which is 2 weeks from today. We've got content today, new content next week, then we're going to review, and then we'll have the exam. The exam will be just like the last time. And as I get more of that exam written, I'll share more information with you guys about the details and like, hey, here's good things to look at. Um, but in the meantime, I'm gonna get started talking about the mole. Could everyone add a number to the chat if they've ever heard what a mole is outside of this class, and a letter to the chat if you've never heard of the mole as it stands in a chemistry class, as opposed to like the animal? Okay, so I'm seeing I would put it at most people are putting a number in, but there's a handful of folks who have never heard of a mole. Um, I'm going to say what like every single chemistry instructor will always say, and that is a mole is an amount. Um, does anyone know? And I like to bring this up because there's all these like if you if you see a group of fish, what is that group of fish called? Or dolphins, I think, is the same thing. A school. Yeah, it's a school of fish. Um, what about if you see a bunch of crows, the birds? Does anyone know what a group of crows is called? A murder. Yeah, a murder of crows. I've always thought that's the funniest thing. Now, with that said, these terms like a school of fish is just basically a group. Now, the exact number isn't really defined. A murder, murder, of crows is also a group of them. Now, I like to bring these up because these are examples of like words that represent something, represent a number. Now, in these two cases, a school of fish and a murder of crows, and I'd have to look into this a little bit more, but I don't think that they're defining a single number. Like, if you have 15 fish together, that does not make a school of fish. I think that if there's like 6 to 8 to 20, that would be called or referred to as a school. Now, when we think about a number like a dozen, well, a dozen is an exact defined number. So this is a defined DEFINED. And that defined number is 12. So there's things that you can say that are like you can almost make this sort of circular. If you have 12 um, phones, that would be the same as saying you have 1 dozen phones. If you have 1 dozen phones, that is 12 phones. Phones. If you have 12 dozen phones, could anyone tell me how many phones that is? 144 phones. Perfect. Okay, so if you have multiple dozen, then you have, well, that multiple times 12 that you have to use to come up with that total number. Now, we do the same thing when it comes to a mole, but this number is crazy large. Now, if you remember when we have this times 10 to the 23rd, that brings back scientific notation. If I write the number 6.02 times 10 to the second, could anyone add to the chat what that number is in full notation without the scientific notation? Yeah, this is 602. Okay, so then if I were to write 6.02 times 10 to the sixth, well, then we're moving our decimal place 1, 2, 602, and then we got to have 4 zeros. 3, 4. Because 1, 2, 3, 4, 5, 6. So if we have a times 10 to the 23rd, that would basically be the same as 602. Could anyone tell me approximately how many zeros should be after that 602? 21. 21 zeros. And I'm going to save us all the time and not write those zeros because that's going to take a lot of time. If you want to, I think that it's a good exercise to sort of connect your physical writing with that number and how large that number is. Now, just to also go back to, well, let me go ahead and write this out. 21 zeros. Could anyone tell me what this number is? 6 zeros. Yeah, it's a million. Then this number right here with 3, 6, 9 zeros. This one right here, we're looking at billion. If I added 3 more zeros, we're talking about trillions. 3 more zeros after that, quadrillions. So when we are looking at 21 zeros, we're looking at something that would be, let's see, 9 zeros is a billion. I hope this, whenever I write this right here, I'm just emphasizing that as a zero. 9 zeros, 12 zeros is trill. 15 zeros is quadrillion. 18 is, I think that it's pentillion. And 21 zeros, I think, puts us at hexillion or sextillion. I think it's hexillion. So with that in mind, could you give me a 9 in the chat if you follow? Yeah, this is a pretty huge number. or a letter in the chat if you're like, I don't really understand it. Okay. So what I really want to emphasize is when you have a mole of something, you have a lot of that thing. You have 602 hexillion things. Now, that's important, but also if you like, can you see an atom? Like if you look at your hand, can you look really closely and find one of the atoms that make up a protein that makes up one of your skin cells? No. Even the strongest microscopes in the world can't really do that sort of thing. Now, again, this is really emphasizing if you have a mole of something, it's simultaneously or at the same time, it's both a lot of something, but then not very much of something. And that's a tough thing to wrap your mind around. But that's one of the important things that chemists do in order to kind of communicate, well, how a chemical reaction is taking place. Now, with that said, October 23rd is through the American Chemical Society, they always refer to that as Mole Day. Why is it the 23rd? Well, October is the 10th month of the year, and the 23rd is the 23rd day of the 10th month, which this year that would end up being, I think, on a Saturday. Nope, 2 weeks from today. Oh, how about that? We're taking our exam on that day. I don't know why I forgot how to add 14 to 20 to 9, but here we are. So we'll have an exam on Mole Day. Now, this is our first poll question. And with this poll question, what I'd like you to do is um actually now we're gonna come back to that question, okay? Um, so looking at this right here, got a dozen eggs, dozen yellow roses, and dozen nails. If you had to guess, put a Y or an N in the chat. Do all of these weigh the exact same amount? No, chances are slim. Does anyone want to guess which one weighs the most? We'll go with A, B, and C from the left. A, B, C. Yeah, I'm leaning towards A as well. I'm not going to get distracted by the vase holding the flowers. I would bet that those eggs probably weigh the most. The least I would say is probably C, the nails. Now, you have a dozen of all of them, right? Yeah, it's a dozen. So that's kind of strange. One dozen of something, or one dozen of two things, they don't have the same weight. Do you think that if you have a mole of two different things, well, actually, let me go ahead and pivot a little bit. And let's say that you had one mole of eggs, one mole roses, and one mole of nails. First question is, can you imagine thinking about how many you would have to have? You'd have to have 6.02 times 10 to the 23rd, or 602 hexillion of these different things. Um, Again, which one do you think would weigh the most? A, B, or C? Still going to be A, because the number of them has just increased. Now, visualizing that, that's such a large number of eggs that I can't even really wrap my mind around it. Because it makes me think like, oh, well, could they fit in, would how many eggs would fit in the Grand Canyon? I don't know. That's a really strange question to wrap my mind around. But my point here is that you can have a mole of different things, just like you can have a dozen of different things, and they have different masses. Now, looking at this slide right here, this asks us the question, what does a mole weigh? We get this from the periodic table. Now, If you have a mole of copper, it's going to have a mass of 63.5 grams. This is known as its molar mass. Can you give me a Y or an N in the chat if you see how that information is connected to information that's found on the periodic table? Great. Now, if you have 2 moles of copper, could anyone add to the chat approximately what's the mass of that? Perfect. 127, about. You just take this number and we multiply it by 2, or take this number, multiply it by 2. Okay. Now, with that in mind, I'm going to erase this and I'm going to ask you, and one of the things that I always like to do and was very helpful for me whenever I was learning about moles and really understanding what a mole was, it was very helpful for me to add right here of, and right here, before copper and after copper atoms. So I would say 1 mole of Cu atoms has a mass of 63.5 grams. The reason why I did that and what I found, or the reason that I found that to be very helpful was because then I could say, oh, okay, well, what that means is 6.02 times 10 to the 23rd Cu atoms has a mass of 63.5 grams. And if you're looking at this and saying, well, why is he not saying 0.55? I'm just doing that for saving a little bit of time and saving a little bit of writing. Don't get stressed about that and think like, oh, what should I just randomly pick a number? No, no. Your reference is going to be the periodic table, but as you can see right here, I'm using this number right here. Could you give me a Y or an N in the chat if you follow that kind of logic and that approach? Okay. Now, we're going to go back to that poll question that I had a moment ago. And I would like you guys to answer this question. And it's A or B, but disregard options C and D in the poll question. Do these 1 mole samples have the same mass? We've got a mole of copper, a mole of iron, a mole of sulfur, and a mole of mercury. Then in the balloon, we have 1 mole of helium. And the reason that, and just so we're all clear on this, the helium is the gas that is in that balloon. The balloon itself is a different material altogether. So don't look at this and think, oh, wow, I can make a balloon out of helium? That's fantastic. Okay. Now I'll leave this up for just a moment. These 1 mole samples. I'm going to jump back. 1 mole of copper. If I were to put this on a digital balance, it would read out 63.55 grams if it was a good enough digital balance. Iron. I don't have iron, but you know what? I can pull it up on a periodic table. Do I have a chemistry book around here? No, I don't. The periodic table. I got a private message of someone saying, I meant to put B. Don't worry about it. So mole and atomic weight are the exact same thing. Yes, they are. They are. That is a fantastic question. I'm going to revisit that one in just a moment. Fe, it's about 55.85 grams. And then, let's see, we got sulfur is about 32. Mercury is 200. 32 grams, and I'm rounding here, 200 grams. And then helium is going to be about 4 grams. Okay, I'm going to go ahead and close this hole. So my point here is that all of these samples are 1 mole. They have different masses, though. So if you were to pick up the helium, well, you could hold 1 helium or 1 mole of helium. Approximately how many atoms of helium are you holding in your hand if you have 1 mole of helium? 6.02 times 10 to the 23rd. So given the option of lifting 1 mole of helium versus 1 mole of copper, which is going to be easier to lift? He or Cu? Easier lift. 1 mole of He or 1 mole Cu? Helium. Absolutely. Because helium is lighter. And if you are lifting 1 mole of helium, you're lifting 6.02 times 10 to the 23rd atoms of it. If you're lifting 1 mole of copper, you're lifting 6.02 times 10 to the 23rd atoms of that thing. Now, with that, when we look at this right here, it's worthwhile to think about the connection between subatomic particles and molar mass. Do we kind of already know that the mass of, let's say, I'm going to go with aluminum, the mass of aluminum is greater than the mass of boron? Do we know that? Let's think about this. What does a boron atom have in terms of protons, neutrons, and electrons? Could anyone tell me approximately how many protons does 1 boron atom have? 5. What about neutrons? Roughly 10.81, so 5 or 6. I'm going to call it, I'm going to call it 6. And then electrons, if we're talking about a neutral boron, we're looking at about 5 of those. But which of these subatomic particles, protons, neutrons, and electrons, which of them basically doesn't have a mass? Electrons. Electrons are pretty much massless. Okay, now let's talk about aluminum. So let's just talk about protons and neutrons for an atom of aluminum. How many protons does 1 atom of aluminum have? 13. Great. And now we'll round this one up to 27. Approximately how many neutrons? 14. Okay. Now, if you think about a proton, it doesn't have very much mass. 10 protons don't have very much mass. 1,000,000 protons don't have very much mass. But when we're talking about a mole of them, well, then it begins to have some substance and have some heft to it or have some weight to it. So we come up with, or we've calculated an atomic mass average, or average atomic mass of 10.81. That's approximately the mass of 1 atom. And the units that we use, okay, I don't get how you're getting the different number of neutrons. I got that as a private message. Well, that goes back to our talk about isotopes. So this number right here, this 10.81, that's an average atomic mass where we said, okay, well, there's boron with a mass of 10, and that is 5 protons and 5 neutrons. And then there's also boron with a mass of 11, which has 5 protons, and we know that it has 5 protons because if something has 5 protons only, it is boron. However, where they differ is their number of neutrons. So these two are both boron, but they are, could anyone add the word to the chat that these two things are? I'll give you a hint. It starts with an I, and it's not ions. Isotopes. Great job. Okay, so these are isotopes, and that's where that 10.81 comes from because we say, oh, well, 60% of the isotopes of boron have this mass, and 30% have this, and 10% have this. So, long story short, this 10.81 is the average mass of one single atom, but it's also the mass of 1 mole of your average atoms of boron. What I think is, so that's kind of our background explanation for this in terms of, okay, well, what's the most practical thing for me moving forward? Is the most practical thing for you moving forward is to look at this number, this 78.97, and say, okay, if I have 1 mole, Joel, come on, 1 mole of selenium atoms, if I put that in my hand, that's going to be about 78.97 grams. Could everyone give me a Y or an N to the chat if they understand that kind of principle? Okay, great. Now, I've got another poll question. And this is going to be a question that brings up other quantities. So you found a 1.5 pound sample of gallium. 1 pound is 454 grams. Select the true statement below. A is you have exactly 1 mole of gallium, no more, no less. B is you have less than 1 mole of gallium. And C is you have more than 1 mole of gallium. And D is there's really no way to answer this question. I'll give you a little bit of time before I intervene, interfere, talk, whatever. Spoiler alert, it's not D. This is a good setup for the sorts of questions that you'll see on your exam. Okay. So if you have 1.5 pounds and 1 pound has a mass of 454 grams, arguably, one of the things that you could do is you could look at this and say, okay, 454 grams is the same as 1 pound. Give me a Y or an N to the chat if you agree with this point right here. Okay. Now I set this up as a ratio and I set it up as a fraction because, and I'm going to say 1 pounds, because what I want to do is I want to come up with an answer in grams. I want to get rid of the unit of pounds. So I'm going to say 1.5 pounds times 454 over pounds. Now, why am I going to do that? Well, because this 1 pounds isn't that in the denominator? And this 1.5 pounds is in the numerator. If something's in both the numerator and the denominator, what can we do with it? We can get rid of it. So I'm going to say 1.5 pounds times 454. And that will get me, it's like 670 or something like that. 454 times 1.5, 681. 681 grams. Now, this is really just a question of, is 681 greater than or is 681 less than 69.7? Well, 681 is obviously greater than. And we know that 1 mole of gallium atoms has a mass of 69.7 grams. So our correct answer is going to be C. I'm going to end the poll on that one. For those of you who maybe didn't get that right or maybe just put an answer down, and for those of you who understood it, could everyone confirm with a Y or an N, hey, I understand this sort of question? Okay, great. Now, this sort of question can be modified. And a good way for this question to be modified is like this. Rather than saying you have 1 pound, I would say you have 623 atoms of gallium. If I have 623 atoms of gallium, is that so now it's putting in terms of atoms, and do I have a number where I can think about atoms and moles and the connections between those two? Absolutely. 1 mole is 6.02 times 10 to the 23rd. This number right here is smaller than this number right here. So it's fair for me to look at A, B, and C as answer options and say, okay, if I have 623 atoms, do I have exactly 1 mole? Nope, I don't. Because exactly 1 mole is 6.02 times 10 to the 23rd atoms. Do I have less than 1 mole or do I have more than 1 mole? Well, I have less than 1 mole because 623 is a smaller number than 602 hexillion. All right, so that's if we're looking at an individual element. If we are looking at a compound, what we're going to do is we're going to look at the masses of them. And we're going to say 1 mole of CO2. What is that? Well, how many carbons are there? 1 carbon, which has a mass of 12.01. Then we get 2 oxygens. And each oxygen, a mole of each oxygen atom, has a mass of, I'm going to call that 16. So I'm going to say 2 times 16 gives me 32. So 12.01 plus 32, I'm going to round that to 44. That's another kind of next level sort of question where we're looking at assembling all of the different things and adding them up to come up with our answer. Here's another Zoom poll question. What is the molar mass of this gas? I'm going to launch the poll right now. We've got NO2. And as it would turn out, I forgot to put the actual extra answer there. The actual extra answer option there, because 14 plus 32 is 46. The closest to this would be D, but E is the correct answer. So just go ahead and mark D so that you can confirm that you participated in this one. Could everyone confirm that, yes, this makes sense, though, with a Y or an N to the chat? These are all, thank you very much, rookie mistake. I appreciate it. Yeah, I'm like a 13th year rookie. Oof. This is just like golfing. It's a mulligan. No matter what time of the season, you call a mulligan. You're putting, it's a mulligan. Okay. So I'm going to leave that up as I go to the next question, or as I go to the next slide. What you also need to be able to do is convert mass to moles. Oh, I got a question of where's the 32 coming from? Is it because there's 2 oxygens? Yes. Because I round this to 16, multiply that by 2 because there's 2 of them, and that is going to give me the 32. So yes, spot on. Okay. Now, I'll leave the poll question up for just a little bit longer so get an answer in. D is what I would recommend going for. Again, I'm not grading on accuracy, yeah. Um, Here what we have are two different samples. 1.8 grams of H2O and 8 grams of Br2. And I'm going to toggle back and forth. Well, no, actually, I'll do it all on the periodic table separately. The mass of 1 mole to figure this out, what we need to be able to do is we need to say, okay, well, or what we want to answer the question of is how many moles is this? How many moles of H2O? Now, what I'm going to do is I'm going to add one more molecule or one more word. And that is how many moles of H2O molecules? And the reason I'm doing that is because whenever we are over here, nope. It was here. Where is it? Where was that point? Oh, yeah. Where I added 1 mole of copper atoms of an atoms. I like to define that a little bit more. So how many moles of H2O molecules do I have if I have 1.8 grams? What I need to do is I need to look at the periodic table and figure out, well, what is the mass of 1 mole of H2O molecules? And oxygen has a mass of 16 grams. There is one oxygen. Hydrogen, from the periodic table, you would learn that hydrogen has a mass of approximately 1 gram. You might see it as 1.08, but I'm just going to call it 1. But I've got 2 of them. So could anyone add to the chat, what is the mass of 1 mole of H2O molecules? The total mass of this. $18. So 1 mole of H2O is 18 grams. Okay. This 1.8 grams that's down here is just saying this sample or this solution right here is water and it has a total mass of 1.8 grams. Now, my question for you guys is this more or less? Is 1.8 grams exactly 1 mole? Is it more than 1 mole or is it less than 1 mole of H2O? $1.8 grams. Really what we're doing is we're comparing. So let me write my question out. Is 1.8 grams more than 1 mole H2O or less than 1 mole H2O? Or, I mean, third option is it's exactly. So the question is 1.8 grams, is that more than 1 mole or less than 1 mole? Go ahead and answer with an M for more or an L for less. I'm seeing lots of M's here. The question that we're really getting at then is, no, we don't need a periodic table for this because I've given you the mass. 1 mole of H2O is 18 grams. 1 mole is 18 grams. 1 mole of H2O is 18 grams. A lot less. Yeah. So this question, whenever you get to this sort of question, it seems kind of complicated, but what we need to do is essentially look at Okay, here's the quantity that we're given. This is the quantity that we're asking about. And we're comparing this quantity, which I'm putting a star by, to this quantity right here. Could you give me a Y or an N to the chat if you follow how to do this sort of question? Okay. I was getting lots of M's, and I think that it was there either people were mixing up the numbers that you compare, or they weren't sure on what is the mass of 1 mole. So they were just kind of going, yeah, I think it's this. It seems like I've cleared that up though, or we've cleared that up. Okay, so our next question, and I'm going to scribble this number out because what we want to do is we want to figure out first, we're talking about BR2. Okay, let me ask you this and tell me the answer in the chat. How many atoms of Br are in 1 molecule of Br2? Not a trick question, but if you have Br2, how many Brs are there? Two. Okay. So 1 Br, and I'm pulling this from the periodic table, 1 Br has a mass of 79.9. Could anyone tell me the mass of Br2? If you want to round it, you're more than welcome to. 160. I got that as a private message. I'm gonna call it, yeah, I'm gonna go with that 159.8. I know that I just said you could round it, but I'm gonna go with 159.8 grams. Okay. Could you give me a Y or an N to the chat if you understand where that 159.8 came from? So the 159.8, this number right here came from the periodic table. That is the molar mass of Br, and Br2 consists of 2 bromines. So you add the mass of, or you double the mass. So I can go on to say 1 mole of Br2 has a mass of 159.8 grams. Could everyone give me a Y or an N to the chat if they agree with and understand this statement? Okay. So think about this as like, this is like the rule. This is like a reference point. This is a good reference. Now, the question that you would be asked would be something like, well, how many moles are in, or so how many moles of Br2 are in a 8.0 gram Br2 sample? Okay, so what we're going to do with this is we're going to use this 8.0 grams and compare that to this. Okay, could you give me a 1 in the chat if you follow, a 9 in the chat if, wait, what? Okay. So we compare this 8.0 to 159.8. This reference, this 159.8, think about that as our definition. This is our definition. Now, when we look at a number and we compare it to that defined amount, we can ask the question about this 8 grams. Is this M for more than 1 mole or L for less than 1 mole? Add that to the chat. Is 8 less than 159.8, essentially, is our question. Yeah, it's less. Great. So, before I go on to do the math, I'm going to say 8 grams is less than 1 mole of Br2. Add a G in the chat if you agree with that statement and understand how we put it together. Excellent. Okay. Now, what we want to be able to do is calculate the specific amount, calculate the specific number of moles. So how are we going to do that? What we're going to do is we're going to start out right here where I'm putting this little asterisk. I'm going to erase some of this information from the other side of the question. I'm going to say 8.0 grams of Br2. This is the information that we're given by the problem. Now we want to take that information that we're given and compare it to our definition. And I like multiplication, so I'm going to multiply. Now what I'm going to do is I'm going to set up a ratio or a fraction. And I'm going to say 1 mole of Br2. I'm going to leave that up top. And the reason that I'm going to leave that up top is because that is the unit, moles of Br2, that I want to end with. So what I'm going to put below that 1 mole of Br2 is, well, does anyone want to guess what I'm going to put down there? And I'm going to give you a little bit of a clue. This is my definition that's going here. Yes, 159.8 grams of Br2. So the Br2 will, or the grams of Br2 will cancel. Could everyone give me a Y or an N to the chat if they follow that? They follow the setup as I have it right now. Okay. Now, what I'm going to do after this is I'm going to say 8 times 1 equals 8. Done. Then I'm going to divide 8 by 159. So I'm going to go to my calculator. 8 divided by 159.8 gives me 0.05 moles Br2. Now, before we go on, could you add a Y to the chat if you did this calculation in your calculator and you got the same number? Okay. Now, one of the things that I cannot stress enough is when you look at this number, 0.05, whenever you get that number and whenever people get these sorts of calculations, typically what happens, yes, somebody sent me a private message with a more precise number. And yes, I got the same thing. I'm just rounding to 0.05. One of the important things is to look at that number and look at it kind of critically and say, does this make sense? And before you answer that question, then you got to go through your process and say, okay, well, do I have any reason to say, yes, it makes sense or does not make sense? I do. Because I did this step right here where I'm putting, this step right here where I'm drawing some arrows. I already said 8 grams is less than 1 mole of Br2. I came to a conclusion, or actually, does everyone agree with this statement still, that 8 grams is less than 1 mole of Br2? Add a Y or an N to the chat. Okay. I kind of concluded that Well, the number of moles of Br2 that I'm going to get is less than 1 mole. Now, to answer the question of does my answer make sense, is I'm just going to say, is 0.05 less than 1? Wire N to the chat. Yeah. So before I did the actual calculation, I can look at these two numbers and say, oh yeah, those two things, they make sense together. So I like to do that because then you have kind of a reference point. So arguably, if you got this question and if you had an exam question that was this right here that I circled in green, and you had answer options A, B, C, D. And let's say that you had 1 mole. These are your different answer options. Answer option A is 1 mole. Answer option B is 24 moles. Answer option C is 0.05 moles, Br2. And answer option D is 0.5 moles, Br2. And then E is no answer, not possible. Just a little bit of a hint. I like to throw not possible as an answer option in there, and it usually isn't that. Not, just kind of go with that. Now, with that said, yeah, somebody messaged me C is the correct answer. Yeah, absolutely. But when you do this sort of step right here, you can immediately say, well, A is out and B is out. So then I've got two answer options, 0.05 and 0.5. So then if I did the math, I could plug it in and be like, oh, well, it's C. Alternatively, you could look at these and say, okay, well, 0.5 moles of Br2. Well, I know that 1 mole of Br2 is roughly 160 grams. Could anyone tell me approximately what is the mass of half of a mole of Br2? Add it to the chat if you know that. Roughly. Close. It's going to be around 80. Because remember, 1 mole of Br2 is 159 grams. Br2 is a compound. It is a molecule. It's 2 Brs. So 0.5 moles of Br2, well, 1 mole is approximately 160. 2 moles, or sorry, half a mole is about 80. I understand. Yeah. This is a point where you kind of got to check yourself and be like, wait, is it Br2? Is it Br? Okay. I spent time on that because it's important to be able to do this sort of question, converting from a mass to number of moles. The same sort of thing goes here, where we go from 0.1 mole CuSO4 and 0.1 mole of K2Cr2O7. What we need to do first is get the mass of CuSO4. And I'm going to pull these numbers from the periodic table. Cu is 63.5 grams. S is 32 grams. O is 16 grams. Somebody add all this up, and whenever you're ready, put it in the chat. Or when you have the answer, go ahead and add it to the chat. So 63.5 plus 32, 63.5 plus 32 plus, and here's where we got to add times 4. Each oxygen is 16. Absolutely, it's 159.5 grams. So 1 mole CuSO4 is 159.5 grams. Great job. Great job. I think that anyone who got mixed up on that one, what I saw a couple of answers come in as private messages was they came up with 111. And that's where you only added one oxygen. You got to remember to add all four of the oxygens. So that's subscript right there. That says, hey, we got four oxygens. And you know what we're going to do is we're going to say, all right, well, 1 mole is this. Um, let's just go ahead and say, what's approximately 0.5 moles of this? What's the mass of that? 79.75. Yeah. You just divide that by two. Now, um, before we do this, if you have 0.1 of something, let's say, um, if you had a dollar bill and I said, oh, I have a tenth of a dollar. What's that worth? A tenth of a dollar. 10 cents. Okay. So if I wanted a tenth of a mole or 0.1 moles, I could take this number and divide it by what to get my answer? I could take that 159.5 and divide it by 10. Or I could do 159.5 times 0.1. And whenever I do that, I get 15.95 grams. That is this amount. Could you give me a Y or an N to the chat if you understand that? Okay, great. Next up, we've got K2CR2O7. I'm going to give you the masses of each one of these individual atoms, and then I need you to come up with the total mass. K has a mass of 39. I'm going to call it 39.1. CR has a mass of 51. I'm going to call it 52, actually. And then O is 16. I'll do this separately. Whenever you're ready, add it to the chat. 2, 2, 7. Okay, so 39.1 times 2 gives me 78 plus 104. I'm at 182. And that would be, yeah, 294.2. Great job. So that's 78.2. That's 104. And then this is 7 times 16, which is 112. And we get 294.2. Could anyone tell me the mass of 0.1 moles of that? Great job. This is 29.42. So what we've looked at here is we've looked at mass to moles and moles to mass, going in both directions. Being able to do both of these things is going to be very helpful on your exam. Now, the next thing that we're going to do is look at volumes. So converting volume to moles. If you have 22.4 liters of a gas, you have 1 mole of a gas. Looking at all of these different balloons here, tell me with a R, P, or Y, which one of them is closest to 1 mole of a gas? Why? Yeah, you're absolutely right. 20 liters of a gas is less than 1 mole of a gas. That's always something that, for me personally, was tough to wrap my mind around because I was like, wait a minute. If you think about the space, thank you for asking. STP, this stands for standard temperature and pressure. So another way of saying that, I know, and if you're thinking about this in terms of like, where is this taking place? Think about this as like, it's almost like saying sea level. This is being done at sea level. We're not doing this in Denver, or we're not doing this at the top of Mount Kilimanjaro or anything like that, where the temperature is about 23 degrees Celsius, or about 75 degrees Fahrenheit. We're not deep under the ocean or anything like that. It's another way of saying normal conditions or normal lab conditions. Not too hot, not too cold, not high pressure or anything like that. Does that make sense? So the reason that that's brought up is because, well, if you were to, and we'll get more into this a little bit later on, but if you filled a balloon and if you inflated a balloon and you put it in a freezer, what's going to happen to that balloon? It's going to shrink because the space that the molecules of those gases, of that gas, occupies, that is going to go down. Um, Alternatively, if you were in a cold room and you filled a balloon with cold air and you filled it all the way to the top, or you filled it all the way to the brim, and you took it outside and it was 102 degrees, what's going to happen to that balloon? It's going to get a little larger. It might even pop. So that's why we bring up our standard temperature and pressure, or our normal lab conditions. Now, we've primarily worked on this part of this conversion, but we have also touched on this right here. Number of atoms or molecules. 6.02 times 10 to the 23rd atoms or molecules. That is known as Avogadro's number. And that's our way of connecting numbers of atoms and molecules to number of moles. And as soon as we connect something to the number of moles, we can say, oh, well, what's our molar mass of that? Now, from my experience, lots of the questions that I ask about this connection from here to here are going to be the number, or the questions that are similar to this right here. I give you a specific number, 623 atoms. And then I ask the question, well, is that more than, less than, or equal to 1 mole? Now, what you should anticipate would be questions like this: 9.6 times 10 to the 22nd. Is that greater than or equal? So 9.6 times 10 to the 22nd atoms. Is this less than 1 mole, more than 1 mole, or exactly 1 mole? And before you answer that, well, when you look at this exponent right here, what's more important, the exponent, A, or this number right here, B? Add to the chat, A or B, in terms of stressing how large a number is. Absolutely right. It's the exponent. Arguably, the 9.6 doesn't matter. We know that we're going to move our decimal and it's going to go, okay, well, perfect. This essentially is 96 with 21 zeros? Oh, 21 zeros. We've heard that before. Yeah, we have. When our number was 6.02 times 10 to the 23rd. This is the same as 60.2 times 10 to the 22nd. Can you give me a Y or an N to the chat if you understand how to process a number like this versus these? Okay, great. That's very powerful and that's very important. Look at that exponent critically before you look at the other part of the number. Now, the last poll question of the day is this right here. How many atoms of helium are in a balloon filled with 1 mole of helium? And, well, rookie mistake again. Is it 1 atom? No. Is it 2 atoms? Ooh, no. 4? No. Is it 22.4? No. This is a question. E is the correct answer, but just mark D. This is a question where E is correct. What's going on with these different answer options? Okay. D is a detractor. This is a sort of question, or this is an answer option where you're going to see it and you're going to be like, there was something to do with 22.4. Oh man, I can't remember. 22.4. I think I better answer that. Well, yeah, 1 mole of a gas does relate to 22.4. Well, 1 mole occupies 22.4 liters. 1 mole of helium. How many atoms? 1 mole of helium. It's tempting to see this and just be like, oh, well, 1 mole is 1 atom. Done. That's why I'm going to pick A. That's just incorrect. If you know and remember the definition of 1 mole of something, you're going to be in great shape for this sort of question. Now, I can go on to the last one, which is just sort of a preview for what we're doing next time. So this is changing paces a little bit, but what I want you guys actually, before I change, can you give me on a scale of 1 to 5, 1 being I feel great about this entire slide, 5 being I don't feel good about any of this slide, and a 3 being I feel good about half of it, but the other half I need to work on. Could you give me that in the chat? Okay, okay. I think that the part that you should feel probably the best about is this side right here. This other side, the Avogadro's number, what I would focus in on is making sure that I know the definition of 1 mole and know how I can compare these sorts of numbers. And think about this part as like, okay, I'm comparing numbers mostly for these sorts of questions. You'll have questions about this on your homework. So just kind of anticipate that as good practice. Okay, I'm going to close the poll. I'm going to go on to this next slide, and we are going to balance a chemical reaction. Now, if you got to go, have a great day. Thanks for coming to class. I really appreciate it. I'm going to work through these 2 examples, and then this is what we're going to pick up with on Tuesday, because today is Thursday. Have a great weekend, everyone. I'm still going to record this, though. Okay, so we have this compound right here, NaN3. In that compound, in one of those molecules, we have 1 Na and we have 3 N. Okay. Now, that compound, NaN3, will go through what's called a decomposition. It will decompose into sodium and N2. The question is, well, how does it break down? Because if we look on the left-hand side of our chemical reaction, which this arrow right here represents the word yield, which is another way of saying produces or decomposes into. Okay, so that's what that arrow indicates. I'm going to erase all that. How do we have 3 nitrogens? And then over here we have 2 nitrogens. Huh. Well, whenever we're balancing a chemical reaction, the number one thing that you cannot do is look at this and say, well, I'm just going to change this to a 3. You cannot do that because then you're changing the compound or you're changing the substance. A chemical reaction, an unbalanced chemical reaction will tell you these are the two products. There's Na and there's N2. Now, when you do that, what you can do to balance this is say the ratio of the reactant on the left-hand side, and I'll say reactants, to the products. Now, if I put a 2 in front of this is what's called a coefficient. Whenever I put a 2 coefficient in front of NaN3, well then I need to kind of respond to that by adjusting coefficients in front of the other species or the other substances. And so I can balance this by putting a 2 in front of the sodium. I now have 2 sodium on each the left and right-hand side of the reaction. I have 2 Na as a part of NaN3, and I have 2 Na as products. Then what I need to do is say, okay, well, I altered the number of NaN3, so I need to, in response, alter the number of N2. How am I going to do that? Well, this 2 coefficient applies to both this and this. So could somebody add to the chat, how many nitrogens do I have on the left-hand side on this side of my reaction? Whenever I have this 2 coefficient, that applies to this, and it applies to this. So I had some folks write 3, and some folks write 6. I have 6 nitrogens on the left-hand side. So then on the right-hand side, I want to look at the coefficient that I currently have. Right now, the coefficient there is 1. It's not written, so if there's no coefficient written, understand that it's 1. It's not 0 because then you wouldn't write anything. So this 1 coefficient applies to this N2. How many nitrogens do I have on the product side of my reaction? I have 2 because the coefficient before the nitrogen, before the N2, is just 1. I have 1 here because this number right here only applies to sodium. It's broken up by this plus. So 1 N2, I've got 2 nitrogens. How many do I need to have for it to be balanced? I need to have 6. So what coefficient should I switch this 1? What should I adjust it to? 3. Whenever I do that, now all of a sudden, I have an equal number of sodium and nitrogen. So what I changed was my coefficients. Does everyone understand that? Add a Y or an N to the chat. I can change my coefficients. I cannot change my subscripts. Now, for this other chemical reaction, what I want to do is I want to look at my reactants. I've got Fe2O3 and copper. And then I've got Fe and CO2. Okay, so how am I going to do this? Well, I've got a little suggestion here of starting with oxygen. I'm going to put little lines before each one of my substances because I'm going to be adding coefficients. Right now, on the left-hand side, I have 3 oxygens. On the right-hand side, I've got 2 oxygens. I just saw if I had 2 and 3, what's a good number? What's a common product that I can look for? 6. If I can get to 6 oxygens on the left-hand side and 6 oxygens on the right-hand side, they're going to be balanced. Could everyone add a Y or an N to the chat if they agree with that? Okay. So if I were to take a 2 and put that before Fe2O3, how many oxygens do I have on the left-hand side of my reaction? 6 oxygens. So then what coefficient should I put in front of the CO2? 3. Okay. So now I've got 6 oxygens. My question is, are my oxygens balanced? Is the number of oxygens on each side of the reaction balanced? Yes. Is everything else balanced? No, it's not. Well, whenever I put this 2 coefficient in front of Fe2O3, I immediately change the numbers of oxygens. Same thing change the number of irons and oxygens. Same thing goes for this 3. It impacts the C and the oxygens. So basically what I can do is I need to address this and this. Could somebody tell me in the chat what I should put in front of either one of those things and tell me the element or the atom and then the number? I got a suggestion of a 4 in front of the iron and a 3 before the carbon. Yeah. Now, after we've done something like that, I only put a 3 in front of the carbon on the reactants and a 3 in front of the CO2 in the products. Does that work? Okay. Just one moment. So somebody messaged and said, I only put a 3 in front of the carbon on the reactant side and a 3 in front of the CO2 on the products. Does that work? Okay, so essentially what this person messaged is they said they did this. Okay, so first question is, are our carbons balanced? Yeah, carbons check out. Then we've got a 3 that impacts the oxygen. So we got 6 oxygens. And this person who messaged me, I don't think they put anything here because they didn't mention that. So then how many oxygens do I have on the reactant side? 3 oxygens. So 3 and 6 were unbalanced there. Okay, sorry about that. Okay, so what we had a minute ago was a 4 in front of the Fe and then a 2 in front of this. So we want to check after we've introduced something, we always want to check and make sure, does that balance it? We got 4 Fe on this side. We got 6 O on this side, and we got 3 carbons. I always like to draw a little line. We've got 4 Fe, 3 C, and 6 O. 4 Fe, 4 Fe, 3 C, 3 C, 6 O, 6 O. Are we good? I think we're good. Okay, everyone. That's where we're going to go on Tuesday. We're going to be talking about balancing chemical reactions. I hope you guys had a great time in class today. I hope you guys have a great weekend. Big football game on Saturday. I hope you get the chance to go or take advantage if you get the chance to go and have fun with any of the other homecoming related activities. And I will see you guys on Tuesday. Thanks, everyone.